Okay, everyone, here's a recording of assignment number 15. This covers all 4 of our targets. So here we go. Solid magnesium. Solid magnesium, that's Mg, that's a solid, is submerged in a solution of HCl. Solution means this is going to be aqueous. Produces hydrogen gas. Now, hydrogen is a Hofbrinkel, so it's not just H, it's H2, and it's a gas. And we have aqueous magnesium chloride. Now, magnesium chloride is going to be an ionic compound because there's a metal and a non-metal. The magnesium is a 2+ charge. The chloride's a Cl-, it's a 1- charge. We need just as many pluses and minuses, so that'll end up being MgCl2. We are also told that it is aqueous. So overall, let's put those 4 things together. Solid magnesium reacts with hydrogen chloride to produce hydrogen gas and magnesium chloride. I'll go ahead and start doing the drawing part at this point. We'll make the magnesium yellow, the hydrogen, white, the chlorine kind of green. So here's 2 hydrogens stuck together, and then here's a magnesium with 2 chlorines. So immediately we see this is not balanced. There's only 1 magnesium on both sides, and that's good, but here there's 2 hydrogens, and here there's 2 chlorines. So we need another hydrogen, another chlorine. That's pretty easy to fix. Here's another hydrogen. Here's another chlorine. So ultimately then what we need are just 1 of these magnesiums. So I'm not going to draw, but there's a 1. 2 of these HCl's, 1 of these H2s, and 1 of these MgCl2s. So that's 7.1. Here's 7.2. All right, next. 7.3, provide an LOL diagram describing the movement of energy during and after the reaction. So we are told that the solution warms during the reaction. So let's draw this out. So if the solution is going to warm up, that means the energy stored thermally is going to increase. So if I say it starts off with 2 boxes, let's say it goes up to 4 boxes. Then the question is why did the energy go up? Did it go up because we put energy in from the outside? This would correspond to like putting it in an oven or putting it over a Bunsen burner or putting it on a hot plate. We didn't do that. We didn't put it anywhere relatively warm. So this isn't what's happening. Instead, that new energy is there because of a chemical reaction. That energy must have already been here. And all we're doing is rearranging the particles. And when those particles rearrange, some of that energy that was stored in that arrangement gets shifted. So overall, we now have less energy stored chemically than we used to. So this is before the reaction. And this is after the reaction. You can tell that there's been a chemical reaction here because look, ECH changed. If you have a change in ECH, that means that the energy stored chemically has changed. That means that we had a reaction. We also can see that it gets hot. So definitely it's getting hot. And we also see that it's not getting hot because we're putting any new energy in. It's getting hot because of the reaction. Now, will it stay hot forever? No. Eventually it's going to cool back down. So I'm going to show that it does eventually cool back down. It doesn't stay at 4 boxes forever. Things don't stay hot forever. But why did it cool back down? Did it cool back down because of another chemical reaction, which would be what we would show here? Probably not. I think the chemical reaction's already done, right? We already did it. This was the reaction. We don't have another one. At least I didn't tell you about another one. I mean, I guess you could have another one, but I didn't tell you about it. So I think this reaction is done. I don't think ECH is going to change. I don't think there's a new reaction. So where did that energy go then if it's not reacting again? Well, it must have just left. Like things can do that, right? It has gone out into the environment. It's now warmed up the table. It's warmed up the air. It's warmed up the glass. It's warmed up your hand. Just energy that used to be making these particles move faster. Remember, that's what ETH is, how fast these particles are shaking and vibrating. Well, as they run into stuff, they slow down. That's what we're showing here. This is energy that is going out into the environment. It's going outside somewhere else. Because we have energy leaving, this is exothermic. And we would think of energy as a product. All right, 8.1. Okay, every good BCA table starts with your balanced equation, so I'm literally just going to copy and paste this. This year, we won't worry about keeping the energy term, but AChem, that's a thing. So here's our balanced equation that we will start off with. And we need a B, C, and an A. So the B row is what you actually have. So how much magnesium do we actually have? Well, let's go back and look up here. Given a 2.5 gram sample of magnesium. Okay, so we have 2.5 grams of this stuff. Now we are not allowed to just throw 2.5 grams in here because this recipe uses counts. It's one of these, two of these, three of these, four of these. This is not a count, this is a weight. So this recipe just is not built for this. So we cannot use 2.5 grams. What we're gonna have to do is convert that to moles. So let's do that over here. 2.5 grams, where, here, let's go look up the molar mass. Magnesium. I get a molar mass of magnesium of 24.3. So I know that if you have 1 mole, oops, sorry, wrong way. If we have 1 mole of magnesium, that's 24.3 grams. I just got that straight off my periodic table. Or actually, I mean, I'm going to be honest, I Googled what the molar mass of magnesium was. That's okay. You can Google the mass of elements. That's fine by me. But if I take 2.5 divided by 24.3, I end up getting 0.103 moles. This is now a count, right? Remember, mole is just a big number. You're just saying this whole thing is just a really big number of magnesium atoms. It is a count, and that is what our recipe uses. So we're good. We can now use this. So this just goes straight into here, 0.103 moles. All right, I don't know how much HCl we have. We're never told, but I know there has to be some, so I'm just going to mark excess. Remember, that's what we use. Excess just means, I don't know, it has to be there. I'm never told how much it is, so we'll just say that. Enough. So this is us making hydrogen, and I haven't done the reaction yet. So I'm going to say we haven't made any of that or any of this. We haven't made any products yet. So those are the same. Now here, I'm going to use my magnesium. I'm probably going to use all of it. So that's what I'm going to put it here. I think I'm going to use all of my magnesium. I don't see any reason why I couldn't. So if we had 0.103 moles of it, I think we still have, we used 0.103 moles of it and have none left over. Now looking up here, how much of everything else do we make? Well, let's see. 1 magnesium requires 2 HCl's. So it looks like I need twice as many HCl's. So that's what I'm going to put right here. We need twice as many HCl's. So instead of 0.103, I'm going to put 0.206. Now, I still don't know how much I end up with. Even if I use up 0.206, I don't know what I started with, so I can't give you a real good number down here. So I'm just going to put excess again, which again just means enough, right? There was enough there. But we know how much we used. Now, 1 magnesium will make 1 hydrogen. So these should be the same. So one of the tips that I've been telling people is, if you look at these numbers up here, these coefficients, the 1, the 2, the 1, the 1, If the coefficients are the same, well, then the change row has to be the same. If one of these makes one of these, then 0.103 moles of these will also make 0.103 moles of these. Now notice this is positive now because we're making it instead of destroying it. And again, these two are the same, so these two have to be the same. So 0 plus 0.103. All right, so I think that's our entire BCA table, nice and filled out. We're pretty much there, but it's not quite, because we were actually asked a question. The question we were asked was this: how many moles of hydrogen could be produced, and what is the mass of that hydrogen? So let's look down here. So here's my hydrogen. So I need to look in, it's got a little crooked here, but I need to look in this hydrogen column. My answer will be there. The question was, how much hydrogen can we make? I think that's our answer right there. We can make 0.103 moles of this hydrogen. But I want to know what that mass is. So when I need to convert this. So I do ask for the answer two ways. Once in moles, we have that there, that's good. But then also once in mass. So I'm going to multiply this by the molar mass of hydrogen. Now the molar mass of hydrogen for 1 mole, well, I looked it up on the periodic table, and a hydrogen itself is 1 gram per mole. Well, guess what? We got 2. So we've got to double this as well. So 2.02 is what I believe it multiplies out to on the periodic table. Yeah, I think so. When I run that through my calculator, I get 0.207 grams. Technically, if I'm working with sig figs here, because I only started with these 2 sig figs, I should end up with just these 2 sig figs. So I technically should this round up to 0.21 grams, but I think we'll be fine with 0.207 as well. All right, so that's it. That's all 4 of our targets in that one go. This was a pretty easy BCA because so many of the numbers were the same. You'd imagine it gets a little bit more difficult if these coefficients are different, but overall it's still the same general process. All right, everyone, please let me know if you have any questions. Have a nice day.